Hello students, welcome back to the physics class. Today we are going to discuss about a very important topic. Now if you remember, in our first class itself we discussed a simple question that why does a charged hair comb attracts bits of paper. Okay, I told you that time, if you remember, that it is due to a phenomenon of redistribution of charges which gives rise to something called polarization, because paper is an insulator, and in case of conductors the same thing gives rise to induction, right? Now, to explain the concept of polarization in details, or to explain the interaction between polar molecules, like water is a polar molecule, you have learned in chemistry, HCl is a polar molecule, so why they are called polar, what is the meaning of polar here? Okay, and to understand about many such aspects we have to learn this particular concept called electric dipole. So first of all we'll go through what is the meaning of dipole, and then we see the different aspects of it. So first of all we'll come to the definition here. What is the meaning of dipole? So you can see the definition given in the slide. An electric dipole can be defined as a system of two equal and opposite charges, point charges basically, plus minus q, which are separated by a small distance, and we call this small distance as 2L. We include the factor 2 just in order to make the calculation simple, that we'll see in the next part. And this distance is also termed as dipole length. Now remember, whenever we talk about a dipole, you can see that in total the overall charge is 0 because it is plus q minus q. So charge wise it is neutral, but it can produce an electric field of its own, and this is basically due to the separation. So remember, whenever we talk about a dipole, the charge separation is a must. It can be small, it can be large, but it must be there. It cannot be zero. Okay, now in fact what happens is that we may not have only two charges, we can have a complex system of charges also, but if effectively its field etc can be reduced to that of a system of plus minus q, then we can call that this system will behave like an electric dipole. Now whenever we are studying the electric field produced by a dipole, which is also called the dipole field, it can be characterized by, that means its strength, its distribution etc can be characterized by a physical quantity called dipole moment. Now this dipole moment is a vector. As you know, vector has two parts, magnitude and direction. So magnitude of vector is equal to the product of magnitude of each charge and the separation between the charges. Now here we had two charges, plus q and minus q. So what is the value of each charge? Q. So when we multiply q with 2L, the distance, that gives me the magnitude of the dipole moment. What about the direction? The direction is taken along the dipole axis from negative charge to positive charge. You can see in the diagram I have taken the direction as n cap. So when we combine together q, 2L and n cap, it gives me the net dipole moment vector. Now in order to measure the magnitude of the dipole moment, which unit should be used? It's very simple. It will be what? Q is in coulomb, L is in meter, so it will be coulomb meter, right? SI unit. What will the dimension? So coulomb, you know, charge, it is AT, and meter, its length, you know, it's L to the power 1, so we'll get M0 L to the power 1 A1 T1. That will be the dimensional formula of dipole moment. Now here we'll specifically talk about two important terms, two important assumptions which we'll be using very commonly in all the problems, in all the derivations. The first one is called a point dipole, or sometimes it is also termed as an ideal dipole. What is the meaning of it? Now imagine you have one minus q charge, one plus q charge, and they have a certain distance between them. Okay, that is 2L, and we have got some value of dipole moment. Now keep on shrinking the distance, keep on making the distance 2L tends to 0. So obviously to keep the dipole moment fixed and finite, we have to increase the value of q. So in the limit when 2L tends to 0 and the charge q tends to infinity, means 2L decreases to a very small value, q increases to a very large value, and the dipole moment remains finite, then the dipole so obtained is known as a point dipole or ideal dipole. But remember, the length 2L cannot be equal to 0, as I told you in the last slide also, because if it is equal to 0, then the dipole will not be there. Okay. Next, the second one is more used generally. This is called short dipole. So in general, suppose whenever we are measuring the electric field due to a dipole, we take the origin or the reference point as the center of the dipole. Center of the dipole means the midpoint of minus q and plus q, the line joining minus q and plus q. Okay, now suppose the required point is at a distance r from the center of the dipole, and this r is very large compared to length of the dipole. It is very large compared to 2l or l. Then the dipole will be termed as a short dipole. So these are the two important approximations that you have to keep in mind. So basically now the question is, now you understood that why some objects like water molecule etc. are called polar. Why? Because they have a net dipole moment of their own due to their structure. Okay, there is a charge separation. Now question is how to distinguish between a dipole and a simple object. You know, when the object is neutral, when the net charge is zero, okay, simple, suppose a neutral atom, it does not produce an electric field. Okay, we cannot have any force of attraction or repulsion due to it on other bodies. But if it is a dipole, then total charge is zero, but there is an electric field. Okay, so obviously you have to understand why that is happening or how much is that field. So we are talking about electric field due to an electric dipole, which is called dipole field. Now the general case is very complex, but we will take two simplified versions of it, two special cases of it. The first one is field at an axial point. Axial point means, as I told you, that the line joining minus q and plus q is termed as axis of the dipole. So whenever the point lies somewhere on this line, we call it an axial point. Now if you see in the diagram, O is the center of the dipole. We have represented a blue vector P in bold. Again, remember, bold means these are vector quantities. So this dipole moment is being shown by the vector P here. Okay, and we have taken the dipole along the x-axis. You can see minus q and plus q. The direction from minus q to plus q is going from right to left, so it will be along minus I cap. Okay, the distance between the two charges is 2a, right? So if you multiply 2aq and minus I cap, it gives you the dipole moment, which is P. So that I have written, you can see the highlighted part. Now we need to calculate the electric field at the point A, which is at a distance r from the center O. Okay, now you know that dipole consists of two charges. So total electric field at A will be how much? Vector sum of electric field due to minus q charge plus the electric field due to plus q charge. That is from principle of superposition. So let us first find out what is the electric field intensity at A due to the minus q charge. You remember what was the formula for electric field due to a point charge? It was 1 by 4 pi epsilon naught, value of the charge divided by square of the distance. Now you can see the distance between q and minus q is 2a. So distance between center and minus q will be how much? A. From the center, distance of A is r. So what is the distance of A from minus q? It is r plus small a. Okay, so the electric field will be how much? 1 by 4 pi epsilon naught q, that is value of the charge. Remember, I told you that in the magnitude part we don't include the sign, divided by r plus a whole square. What is the direction? So as minus q is negative and electric field means force on a unit positive charge, so the force will be active, that means towards minus q. Towards minus q is meaning towards right hand side, that means along plus I cap. Okay, I hope it's clear. Now coming to the second part, electric field intensity at A due to the plus q charge. Same way you can find out, only the distance will become r minus a and the direction will become minus I cap. So what is the resultant field intensity at A due to the dipole? So as I told you last time, add the two contributions, E due to minus q plus E due to plus q. Resultant we will call as E axial. So now just we are putting the values. If you put the values, you can see the term q, the term 4 pi epsilon naught and the term I cap can be taken as common. Okay, now rather minus I cap we are taking as common. Why? Because you can see obviously the term r minus q by r minus a whole square will be more than the term q by r plus a whole square, because we know that when the numerators are equal, then the fraction is more if the denominator is versa. Okay, so one is plus I cap, one is minus I cap. So we have taken the minus I cap term as common. Why? Because its magnitude is greater. So we are just simplifying. So it will be 1 by r minus a whole square minus 1 by r plus a whole square. Now take the LCM and simplify. So in the numerator now you are getting r plus a whole square minus r minus a whole square. And in the denominator what you are getting? a plus b, a minus b, it gives you a square minus b square, so r square minus a square, and then there is a whole square. Now in the numerator you have a plus b whole square minus a minus b whole square. What is the formula? So a plus b whole square is a square plus b square plus 2ab. A minus b whole square is a square plus b square minus 2ab. So subtract 2ab minus 2ab will give you 4ab. So 4ar, right? Now out of this 4, let us keep 2 aside and let us combine 2qa minus I cap together and keep the r separate. Okay, why we are doing this? Because if you remember, 2qa minus I cap was the dipole moment vector p. So what do we get? We get 2pr by 4 pi epsilon naught r square minus a square whole square. So this is the resultant formula for the axial field of an electric dipole. So again, remember that I told you that for the dipole field to work, the separation between the charges is compulsory, otherwise the dipole will simply behave like a neutral atom. So here you can see if r was 0, okay, if the value of r was 0, right, then what will happen? Okay, so if r was 0, that means if you measure the field at the center of the dipole, obviously the electric field will be 0, number 1. Number 2, if the length of the dipole was 0, if a was 0, what will happen? Dipole moment itself will become 0 and the electric field will remain as 0 only. So for the dipole to produce electric field, okay, to distinguish between a dipole and a simple neutral atom, we must have a separation between the center of the positive charges and center of the negative charges. Whenever this is true, then it will behave like a dipole. Otherwise it will not behave like a dipole. Now obvious question is, why does an atom does not behave like a dipole although it has positively charged nucleus and negatively charged electrons around it? Because the center of the negative charges coincide with the center of the positive charges, that is at the center of the nucleus. So overall it does not become a dipole. Now if the point r is very large compared to a, that means if it is a short dipole that we have learned in the third slide, or if the point, the field point where you are finding out the field, that point is at a very large distance compared to the length of the dipole, then what will happen? Obviously a square will be negligible in comparison to r square. So we can write it will be nearly equal to r square, square means r to the power 4. So when you put back into the formula r by r to the power 4, so you will get r cube. So E axial will be 2p by 4 pi epsilon naught r cube. Now remember this factor carefully, that approximately the electric field of a dipole satisfies inverse cube law. What was the electric field of a point charge? Inverse square law. So this is the basic difference between the electric field of a point charge and a dipole. That means if you move away from a dipole, then the field will decrease more sharply as compared to the field of a point charge. So now we are coming to the second case, that is field at an equatorial point. What is the meaning of equatorial point? The point lying on the equatorial line. Equatorial line means the perpendicular bisector, right? The line which bisects the length, means dipole length, and passes through the center of the dipole, that is known as perpendicularly, that is known as the equatorial line. And a plane passing through such a line is called equatorial plane, that you can see in the diagram. Okay, so as we are finding the field on the equatorial point, it is obvious that all such points will be at equal distance from plus q and minus q, because you know that whenever we take points on the perpendicular bisector, it must be at the same distance from both the ends of the line segment. Okay, so let us take the distance of the required point, that is capital A, from the center as r. Length of the dipole is 2a as usual. Axis of the dipole is again along the x-axis. Dipole moment is again along minus I cap. So everything remains the same, only we have shifted the point, right? So now you can see that we will first find out electric field at A due to minus q charge, following the same procedure. So what will be it? So it will be q by 4 pi epsilon naught, and the distance will be q to a, minus q to a. What is that distance? So you can use Pythagoras theorem, root under r square plus a square, because O to q distance is a. Okay, whole square of it. So obviously root and square will cancel out. You will get q by 4 pi epsilon naught r square plus a square. What is the direction? So as minus q is negative charge, electric field means force at positive charge. That means it will be attractive force. So direction will be from a to minus q. Same way you can calculate the electric field at a due to plus q charge. Value wise it will be same, because the value of charge is same. distance is same, but the direction will be from Q to A because it will give rise to a repulsive interaction. So now the next step, so total field will be E due to minus Q plus E due to plus Q, but you can see the magnitude of E due to minus Q and E due to plus Q are equal. Let's say both are equal to E. So how much will be the resultant magnitude? For that, we have to find out the resultant of two vectors. So we have to use parallelogram law. What was the formula for resultant vector in parallelogram law? Magnitude of the resultant vector formula was root under a square plus b square plus 2ab. So how much will be it? Root under e square plus 2e multiplied by cos 2 theta. Why we are getting 2 theta? You can see that if the line OA makes angle theta with the dipole axis, then QA makes theta with the dipole axis, then minus QA will also make the same angle. Why? Because the distances are same, because it lies on the perpendicular bisector. Now if the angle AQ minus Q is theta, then the angle you can see EA and E plus Q, that will also be equal to theta, because these are corresponding angles. Same way you can find out the other angle, okay, it will also be theta. So total angle between E minus Q and E plus Q will be theta plus theta, 2 theta. Okay, that is why we are getting 2 theta here. Now simplify. So E square plus E square is 2E square. There also we in the second term or third term also we get 2E, so we get 2E square. So you can take 2E square as common. So what do you get? 1 plus cos 2 theta. Now we have learned in class 11th also that 1 plus cos 2 theta is equal to 2 cos square theta. Okay, I'm repeating once again, 1 plus cos 2 theta is 2 cos square theta. Now 2 into 2 is 4, square root of 4 is 2, square root of E square is E, square root of cos theta. So just simplify. Now put the values. Value of E was how much? 2q by 4 pi epsilon naught r square plus a square. In the last slide you saw that. Cos theta is how much? See in the triangle, a by root over of r square plus a square. Now here in the first term, r square plus a square has power 1. In the second term, r square plus a square has power 1 by 2. Square root means power half. So what is the total power? 3 by 2. So we get the magnitude of E equatorial equals to magnitude of P by 4 pi epsilon naught r square plus a square to the power 3 by 2. Now, if you see the parallelogram, application of parallelogram law carefully, then the resultant field is coming from left to right, but the dipole moment direction was from right to left along minus I cap. So you can see direction wise, the equatorial field is in the opposite direction of the dipole moment. So therefore, we are incorporating a minus symbol when we are writing in the vector form. Once again, if r is very large compared to a, what will happen? Then E equatorial will be equal to minus p by, in vector form, minus p vector by 4 pi epsilon naught r cube. Why? Because we can neglect a square. So if you compare the magnitudes, you can see the axial field for a short dipole or for a point dipole, the axial field will have twice the magnitude of the equatorial field, because it was 2p, here it is only p. Now, the next part is very important. We are discussing about what? The effect of an external uniform electric field on an electric dipole. External means, see, dipole also produces a field, but we are not talking about that. We are talking about the field due to some other agent. So let us remember, let us just consider here that we have applied a uniform electric field. That means all the field lines are parallel and pointing in the same direction. That electric field is E. Again, you can see capital E has been bolded. That means it is a vector quantity, right? And have minus q and plus q. The angle between the dipole axis, that means line joining minus q and plus q, and the electric field E is theta, right? Now, as there is an electric field, there will be force on the charged particles, that we have learned yesterday. Okay, in the last section, in the last class, we have learned that. Okay, now. So what is the force on the positive Q charge? It will be Q multiplied by strength of electric field, which is E. Okay, and this force is acting in the direction which is along the direction of electric field. I told you last day that the direction of force will be same as electric field for positive charge, and direction of force will be opposite to electric field for negative charge. So for positive charge, it is along the field QE. For negative charge, it is QE in magnitude but in the opposite direction. Okay, so you can see now the total force on the system is 0. QE minus Q, the total force will be 0. So the system will not translate, it will not move from its place. But these two forces, equal and opposite forces, are acting along parallel lines. And you have learned in class 11 that this kind of a system is called couple. And whenever we have a couple, we have a torque. Right? So due to this torque, what will happen? The dipole will try to rotate. How much is torque? If you remember, torque is equal to, whenever we couple, torque is equal to what? The product of each force and the perpendicular distance between the line of action of the forces. Okay, so what is the product of each force? QE. Now, total distance between minus Q and plus Q was A. Okay, now if you extend the plus QE or minus QE line and if you drop a perpendicular on it, right, then the perpendicular distance will be how much? It will be equal to 2A sine theta. Okay, we have learned this kind of thing in last class. In class 11th, we have learned how to calculate torque of a couple. So you can just note it down in a paper and try to find it out. It's very simple, 2A sine theta. So what is the total torque? Total torque, Q 2A E sine theta. Now what is Q into 2A? It is nothing but value of the dipole moment, magnitude of the dipole moment, that is small p I have written without the vector symbol. So it will be P E sine theta. Okay. And obviously as torque is a vector quantity, we can write in vector form as tau equals to P cross E. So remember, whenever the dipole is along the field, okay, along the direction of E or opposite to direction of the E and E is uniform, then the torque will be 0, because for theta equal to 0 or 180, the value of sine theta is 0. Right? Now what this torque will try to do? For any other angle there will be a torque. What this torque will try to do? It will try to bring the dipole along its direction. So remember, whenever we place an electric dipole in a uniform external field, it experiences only a torque, and this torque tries to decrease the value of theta or keep the dipole along the field direction. Now the last slide was the case of uniform field, but generally every time the field is not uniform, right? So what will happen if we place a dipole in a non-uniform field? For that, we are taking two simple cases. Let's see the first diagram. What is given? We have minus Q plus Q, right? So dipole moment is from left to right, and the direction of the value of the electric field is increasing from left to right. That means electric field magnitude at the location of minus Q is less and at the location of plus Q is more, and the direction of field is along the left to right direction. So obviously what will happen? You know, the force on plus Q charge will be along the field. It will be greater. Why? Because at that point the value of field was more. Okay. The force on minus Q will be opposite to the field. It will be smaller. You can see that length of the force on minus Q vector is small and length of the force on plus Q vector is large, right? Because the magnitude of field at location of minus Q was less. So in which direction net force will act? Will the net force be 0 now? Obviously not. Why? Because the two forces are not equal. Which one is more? The force on plus Q is more. So obviously the total force on the dipole will be along the direction of increasing field. Whenever we place an electric dipole in a non-uniform field so that the dipole moment vector and field direction are in the same direction, then what will happen? The dipole will tend to move along the direction of increasing field. Now, will there be a torque on it? Obviously not. Why? Because the angle between P and E is 0, and you know sine 0 is 0. Okay, so basically there is no torque. Why? Because both the forces act along the same line, and you know that in the formula for torque we had R cross F. So when R and F are in the same direction, the torque will be 0. Now let's say in the opposite case, that means the electric field is applied from left to right. It is increasing from left to right, but I have kept my dipole in the opposite direction. That means dipole moment is from right to left. So now what will happen? Force on minus Q will be more, but force on minus Q is in the right to left direction opposite to field. Force on plus Q will be less, which was along the field. Okay, so in the opposite direction force will be greater. So obviously what will happen? The net force on the dipole will be from right to left opposite to the field. So the dipole will tend to move in which direction? The direction in which the electric field was less. So whenever we place an electric dipole in a non-uniform field so that the dipole moment is opposite to the direction of E, what will happen? It will tend to move along the direction of decreasing field. Okay. Here again, the total torque will be 0 on the dipole. Why? because here the angle theta between P and E is 180 degree. Again, you can see the two forces lie along the same is 0 using the same logic. Now, for any general orientation, if the theta is not 0 or 180 or 0 or pi radian, except these two cases, whenever there is some angle and the field is non-uniform, there will be a force plus there will be a torque. So the dipole will have a translation as well as rotation. Due to torque, it will rotate. Due to the net external force, it will translate. So that is about the effect of a non-uniform field on a dipole. Now can you tell that why the charged comb was able to attract bits of paper? Now see, paper is what? Insulator. So when you bring the charged comb near it, what happens? Due to the presence of the charge, the positive and negative charges tend to redistribute. I told you in case of induction, in conductors they will actually move. In case of insulators, they will tend to move. They will just have a slight displacement. Now whenever this slight displacement occurs, minus q and plus q, when they are separated, it becomes a dipole. So the electric field of the charged comb induces dipoles in the paper pieces, and as this field is non-uniform, so the dipole experiences a net force towards the direction of the charged comb, and that is how the paper pieces get attracted. So now we can simply, you can say, explain the dipolar interactions with the help of the concepts of dipole field, torque on the dipole, what will the effect of non-uniform field, etc. Okay. So that's all from today's session. Okay, we have discussed the theoretical part regarding what is an electric dipole, what is the nature of field produced by it, what effect is experienced by a dipole in the presence of some external field, what if the field is uniform, what if the field is non-uniform. Okay, we'll have some examples and questions based on that, which you'll find within with the notes available. Okay, so that's all for today's session. In the next session, we'll discuss about electric field due to some more complex cases, and we'll discuss about some continuous charge distribution in the next segment. So thank you so much.